Hello and welcome to our capstone overview video. Our capstone project titled Application of Electrodialysis to Treat Brackish Water for Agricultural Irrigation was performed by 3 University of Cincinnati environmental engineers, Adam Chalazinski, Zach Spangler, and Alex Watzek, alongside 3 UC mechanical engineers, Lisa Barkalow, Zach Jones, and Jason Lorah. This project was sponsored by Dr. Mohsen Rezayat and his philanthropy organization, OMID.
Through our testing, we think electrodialysis, also known as ED, could be a great alternative to high-pressure reverse osmosis systems to desalinate brackish water. ED utilizes the concept of metal plates located on both sides of a membrane stack consisting of anion and cation permeable membranes located on either side of a flow channel. As the feed water passes through, the charge from the plates causes salts to be stripped through the membranes to a brine stream. The brine stream can also be recirculated through the system and inputted into the brine channels with a secondary pump. This helps to prevent membranes from drying out, as well as promote further osmosis of ions into the brine stream and water molecules back into the feed stream. The feed water is continually recirculated until sensors measuring salt content in the water has reached a preset value, either ready to directly apply to a farm or be prepped for a nutrient injection system before heading out to a field.
All right, good morning. I'm Zach.
I'm Zach.
We're going to walk you through our little pilot system right here. Okay, so right here, as you can see, the entire system is independent besides from our monitor here. In the full scale, this will be a phone. It's an app on Android right now. Everything else is running independently on solar power. So we've got our app with our running sensors. Okay. Raspberry Pi contained in this 3D printed box. All right. It's connected to these sensors. So we've got a conductivity and a pH sensor on a float. So it sticks in the tank, and it is constantly measuring every 10 seconds, conductivity and pH levels. Okay, we do have our system split up into 2 different circuits. So you see the heart of our AC circuit contained right here. We've got our solar panels on the back here being lit by a grow light to this charge controller. Charge controller is charging our battery, which is powering our inverter underneath. The inverter is running our pumps.
The pumps are what we use to supply water through our brine tank and our feed tank to the electrodialysis cell located right here. The electrodialysis cell takes the salt out of the water and cleans it, brings it to a more normal salinity. And then this dirty water is going to go back into the brine tank. The clean water is going to go through a UV filter, UV light, where all of the bacteria is inactivated. Once it's inactivated, it goes back into the feed tank and recycles until we reach a level where the salinity is acceptable to the farmers.
Right. On the other side of the system, you can see the other half of our electrical components. So our 2 panels on the other side here are connected directly to our electrodialysis cell. They are what's charging, putting the positive and negative charge on the plates to remove the salts from the water. So AC panels, DC panels. That's it for our pilot system. We really hope you like it.
The sensors are queried every 10 seconds using cheap consumer grade hardware and sensors and a Raspberry Pi here. And then all of the information is sent to a SQL database using a Python script here that's stored on the Pi. And then the app uses PHP, so it's just rendered in your browser, so it's cross-platform. It can use any mobile device. And this renders all of the database information just using Bluetooth, so it does not require internet access. And then from the app interface, you can manually control any of the pumps. You can set them to auto run, which means it will operate depending on the sensor settings. And you can control any of the settings here, any of the high or low alarm temperatures for any sensor metric, and you can update, sensor frequency and delete values in the database. and operate everything from your mobile device.
Pictured here, we have the results from our electrodialysis bench scale system. As you can see by the plots, all of the trials trended downwards for electroconductivity, which means the salinity gradually went down throughout the trial run. Each one was about 120 minutes, but most of them we cut short after 90 minutes because the salinity got down to below our threshold. We originally ran under standard conditions, which was about 0.6 gallons per minute flow and 48 volts for power. Our various trial runs consisted of lowering the voltage, raising the salinity of the starting feed water, and also lowering the flow rate. But in each of the different scenarios, the salinity went down over time. The overall results for all of the trials showed an average reduction in salinity of about 87%. Our highest reduction was 99.6, which is a huge reduction over time, and that was starting with a high salinity of over 1,400 microsiemens of electroconductivity. So overall, our bench scale treatment system showed that electrodialysis is a viable treatment option for brackish water.
Okay, so now we'll go into a little bit more detail on the circuitry of the system. So we split it up into an AC circuit and a DC circuit. As you can see, the DC circuit really is very simple. It is just the solar panels directly connected to the electrodialysis cell, with the potential for including a switch for when you want to turn off the system in the evenings. And then for the AC circuit, it's much more complicated because the solar panels initially produce DC power, so that has to be converted. So we'll run through this system. You connect your solar panels to a charge controller, which then connects to a battery. This charge controller monitors and protects the battery, as well as providing backflow current protection for the solar panels. The main purpose of our battery is so that we can keep the app and the sensors up and running after hours, as well as do extra UV treatment after hours as needed. So the battery connects to the inverter, which is what does the converting of DC to AC power. And then the inverter, you're able to just directly plug in like normal outlets. So you can plug in your UV light, the water pumps, and all of the app and sensing equipment. So that's really all it takes to power the system.
Our full-scale system design follows the same principles as our pilot system. We wanted our system to be fairly flexible. To keep things economical and scalable, we decided to plan for a 2,000-gallon storage tank. The idea is to be able to treat the water through the system through the peak sunlight hours in the day to utilize all of the solar power directly. Our full-scale system consists of a multitude of different components, such as solar panels, solar charge controllers, batteries, inverters, pumps, UV system, electrodialysis cell, sensors such as EC sensors, pH sensors, temperature sensors, and pressure transducers, along with pump thermal overloads to protect pumps from running dry, and a microcontroller to act as the brains behind everything. We estimate our scaled up version is around $18,000 to treat 2,000 gallons daily.